Yeah, I'm going to present the GNU radio and the Universal Software Radio Peripheral. It's not about animals or anything like that. It's just a historical name, which I won't go into. And GNU radio and the Universal Software Radio Peripheral is a complete software radio system or platform that is, in my opinion, very different from other software radios that you may know or have used, at least in the ham radio domain. Because it's not an off-the-shelf, ready-to-go product that you download, install, push a button, and you're on the air. No, it is a framework which will allow you to build your own software radios. Okay. To me, it all started when a few years ago, when I decided, okay, I knew nothing about software radios, but everybody was talking about it. So I said, okay, I want to learn everything there is to know about software-defined radios. And at the same time, we saw cell phones doing high-rate data transmission on gigahertz. So I wrote down a few requirements for my next radio that I wanted to own. And I'm sure you can see that this was not a radio that I could find in the ham radio shops around the world. So I had to look somewhere else, and I took a look at the consumer electronics market, and that's where I found GNU radio and the Universal Software Radio Peripheral. Now, how does all this fit into the software radio framework? I assume that all of you have at least heard about software radios, okay? There's really no time to go into details or the basic details, but if we start on the left side, we have an RF front end, okay? In particular, if you want to work on microwaves, bits and bytes cannot fly, so we need some RF to put them on the air. And the RF front end basically converts between analog RF and analog baseband. Baseband is your spectrum converted down to 0 hertz, plus minus half your bandwidth. In the middle, it's what is actually called the Universal Software Radio Peripheral, acronym USRP. It's easier to use. And that does much of the work in terms of converting between the analog and the digital domain. So that's where really the high performance work is done. And it also does a lot of resampling because the ADCs and the DACs are usually running at a very high frequency that our computers are not able to process. At the right side, we have a standard laptop like this or that running the software radio itself. This is usually limited to lower rate processing. Let's say I wrote 16 megasamples per second, which is specific for this setup. It can be anything from 10 kilohertz to, I don't know, 20, 30 megasamples are probably possible in today's computers. This is a closer look at the Universal Software Radio Peripheral itself, the main board. As you can see, it has an FPGA in the middle, and this is where the conversion is done, or the downsampling of wideband to narrower band, because it has a USB interface to connect to the computer, and that poses limits on how much data we can transfer. USB 2 is 480 megabits per second, but when you take all the protocol and things away, you end up with about 32 megabytes per second for use. And that allows up to 8 megahertz of complex signals or bandwidth. In addition to that, it has also, so it has main analog to digital and digital to analog converters. That's what you see on the two sides of the board. And the two white connectors are where you mount the RF front-end boards. You can see there is RXA, RXB, TXA, and TXB. It means that it can take two receivers and two transmitters and use them at the same time. Okay, two transceivers. And the only requirement there is that they have to share the 8 megahertz of bandwidth. So it's still pretty good. Now I have a quick example for an RF board, which is called daughter boards in the USRP terminology. It's called WBX. It's one of my favorites simply because it covers 50 megahertz to 2.2 gigahertz. Okay, no band switches, nothing. one continuous coverage, 50 megahertz to 2.2 gigahertz, to tune via software. It's a full duplex transceiver. It has a quite good direct conversion receiver. You can see the noise figure is around 5 to 6 dBs, depending on which end of the band you are. And it can even give up to 100 milliwatts of transmitter power. So it's very good. It costs around $450, I think, but I think it's good value for money. So the last piece in the puzzle was GNU Radio itself, which is the software platform for doing anything with all this hardware. And it's a very large and complex system, no doubt about that, but it can be regarded very easily as, or in simple terms, as on one hand consisting of a signal processing library. If you want to build software radios, you're going to need functions for filtering, modulation, input-output, a lot of utilities, so all these are organized in the library. And on the other hand, we have an execution framework, because you have to connect all these blocks together so that they run in a continuous data flow way, right? Just like a hardware receiver where you have the signals coming in on one end and going out on the speaker. Same with software radios, except that it's very difficult to emulate the real-time behavior of hardware in software, in particular when we get up to high data rates. It's a challenge, but GNU Radio has a very good framework for organizing all this and taking care of every single core you may have in your brand new multi-$1,000 computer. It will make sure that everything is used. There are 3 levels to, we are talking about writing software, okay, so, but please give it a chance. It's just stay with me for 10 more minutes, okay, or 5 more minutes. It's the lowest level is C++, because this is where all the fundamental blocks are implemented for performance and efficiency reasons. Filters and the expensive modulators, they are implemented in C++, and if you're a fanatic, you can actually go in and write C++ applications. Fortunately, all the C++ functions are exported to Python, which is a higher level scripting language, very easy to use and learn, and that is pretty much where most users of GNU Radio work. They prefer writing Python applications because it's easier, and it doesn't cost anything in terms of efficiency, because what they do is to connect all the blocks that have been implemented in C++, so there is no penalty. If you're like me and even lazy to write Python code, there is a graphical tool called GRC, the GNU Radio Companion, which will allows you to sit back in your chair and design these flow graphs in a graphical environment. And yeah, we'll take a look at that in just a moment. First, a quick Python example. I'm not going to make a line-by-line walkthrough. It wasn't my intention. It's just to show that it's not rocket science. Okay, this is a complete program for generating a dial tone with 2 frequencies. And what's important to note is that there are 5 lines which are actually where the whole graph or the whole application is built. There are, you create 2 signal sources. It's a sine wave, yeah, the frequencies. Create an audio sync and connect them together, execute, and you have the tone in the speaker. The very same program in the GNU Radio Companion, the graphical tool. You see, you have on the right side, you have the collection of the library, the blocks which you can use. You click on them, drag them over, and connect them with arrows. There are arrows, so it shows which way the data flows, and it's pretty much the same. Once you are done, you click on one button, it will generate the Python code for you. And surprisingly, it's very clean and readable Python code. You can press the other button and it will even start running the application until you stop it. So that was a 10-minute crash course in GNU Radio. We are now ready to build something, right? Let's start with an FM receiver. Just to illustrate that it's really no big deal. And for those, in the sense that if you are, you know, many people, I say, oh, computer software, no way. It's it takes some time to start and get started and learning it, but once you learn it, you see it's really simple. It's like drawing a block diagram of a hardware radio, okay? On the, it's your left side, yes, there's a USRP source, which is the interface to the hardware. It's like a driver. It gives you the data stream from the hardware. There is one arrow going up to an FFT saying this is a must in software radios. It will simply display a spectrum display, and if you don't have that, then I don't think you can call it a software radio. You need some graphical fanciness, right? And so it will show the raw spectrum. The bottom graph continues, goes through a low-pass filter, a block called NB-FM receive, which is actually a composite block built out of all the necessary, the de-emphasis, the demodulator, and an audio filter. And out of that, you have the audio, put an audio amplifier, and out to the audio sink. This is not just an academic example. It is a real receiver. It works, and you hook it up to the USRP and put an arrow antenna on it, and you can start receiving amateur radio satellites. Let me try if I can get the sound on. Not that it's interesting, but it's packet radio from the ISS received just recently. It's a little more extended than the example I showed you because I connected to an external software modem to also decode the packets. Now I don't know if you noticed it, but there's actually also another satellite in range at the same time. It's VO52. ISS comes here, VO52 goes there. I didn't know about it when I pointed up the antenna. I just saw something was wrong on the spectrum. And that's what you can see on the right side here. It's the downlink of VO52. Yeah, that was a good spin-off, and it's a software radio, and fortunately I was recording the spectrum so I could go back and listen to VO52 afterwards. I had to make an SSB receiver, of course, but that's small details. Transmitting. You also want to transmit, right? And as you can see, it's really, really difficult to create a transmitter. You need actually the same amount of blocks as for the receiver, and it just goes the other way around. Start with the audio source. Have the transmit block is already implemented by other people. Okay, we are not the first ones to want to make an FM transmitter, so it's you just take it, put it in, connect to again an amplifier to bring the data level up to what the USRP requires, and put it on the air. Now, what do you think will happen if we take this? Imagine we are in the application, okay? We mark everything, press Control-C, copy, go back to the receiver graph or program, and press Control-V, paste.
Transceiver.
Exactly. Not only a transceiver, but it will be a full duplex transceiver, completely independent receiver and transmitter parts, and yeah. So that's, yeah. I mean, I just sometimes I hear people talking about, yeah, but it's difficult because my radio is not full duplex. But okay, yes. Now I think it's about time that I come with a warning, because GNU radio is very, very dangerous. Once you spend the time to get started and get the hang of it and are able to create something that actually works, it will really motivate you to get the craziest ideas that you have never imagined you would get. This is how the USRP looks. So we will have it here in the lunch break, and later you can look at it. But see, 4 connectors. As I said, it can take 2 transceivers at the same time and use them at the same time, not just have them. And we are satellite enthusiasts, so obviously, well, why not build a satellite transponder out of it? Okay, we have the hardware, full duplex hardware. What does it require on the software side? Got to be very, very difficult, right? Well, yeah. Okay, it's a dumb transponder, but I mean, you see, you get the output of the receiver, of one receiver, connected to the input of one transmitter block. This, as it's configured, it's 5 kilohertz of bandwidth, and the configuration is actually happening with these numbers here called decimation. I don't know if you can see. And that's because the ADC runs at 64 megahertz, 64 megasamples per second, and the decimation is simply what you divide that rate with to get the final bandwidth. Similarly with the interpolation on the transmitter side, but that runs at twice the frequency. I can tell you this works. I had a lot of fun having it on my desk and using one radio to talk, and I even put a delay line in to simulate as if I was talking with a satellite towards Mars or whatever. It's really fun, but okay, it's yeah, it's fun, and but okay, it's after a while you get bored and get the next crazy idea, or want to make it better because okay, let's say I'm building a satellite. I also want a telemetry downlink and telecommand uplink. So let's try to see what it takes. It's a little more complicated, but I can still have it on one slide, okay? And I think those who sit in the front row can actually see what's on it. We don't have to go into details, but it's pretty much the same, except that I have now limited the band pass to 100 kilohertz of transponder bandwidth. That's what goes on the top. And what comes down is then a channel selection where I select a channel which is located 50 kilohertz below the center, and I use that as a telecommand uplink. This example uses binary phase shift keying, but just as an example. And I think this can actually be run as kind of simulator or demonstrator and actually get data in and out of it. Similarly with a telemetry encoder, it gets telemetry encoded in BPSK, and then adds the two signals together before it sends to the transmitter. So, okay, that was it. It wasn't so difficult, okay? Clearly, it's not a flight-qualified software or anything, but I think for demonstration and for learning, training and things like that, simulating, it's really great. And you can run it with hardware or without hardware. It's, yeah, no, as you wish. Now I have time to get the last part of it. We were thinking, let's try to make something different. It's not much of with satellites, this thing, but still, these days everybody has a webcam, right? And if you go out and buy a webcam today and spend, say, €100 on it, you even get one which can do high definition. Not very good high definition, but the resolution is there. So what if we connect it to one end of a standard PC computer, which, well, I prefer using Linux, and because on Linux you have all sorts of tools to do these kind of quick hacks, okay, just make something work. I had a framework called Gstreamer, which is very much like GNU Radio, except that it's for audio and video processing, and it's already installed and integrated in most Linux distributions. It's what the multimedia players are based on. And connect the radio on the other end. Would it work? Was the question very first. Well, yes, it would, or yeah, it did. And this is the demonstration of it, recorded just a few days ago at 7SET. This is the transmitting computer. You can see the webcam hooked up. Note that the computer doing the encoding, capturing, software transmitter runs at below 25% CPU load. Okay, not high definition, but still. That's the transmitting part, and this is another system, another computer with under USRP set up to receive the data. And there it runs at 640 times 360 resolution. Just because the receiving computer is very slow and would not be able to actually show the high definition. So, okay, I think I will. I have the setup, but I don't think I will go into detail. We better finish up, and you will see it on the slides. You can ask if you're interested, but it was very simple, and just make the pipelines and connect them using a Unix pipe, which is yeah, just an interface between two applications. I included the actual code if somebody wants to try it. What you see on the bottom, that's a command line, a very long one, but that's actually what builds the complete video processing pipeline, okay? One command line, and you have video coming from the webcam. It adds text overlay, compresses and encodes it into H.264, puts it in an MPEG transport stream container, and sends it out to FIFO. Similarly, the receiver is again very simple. The actual video player is even simpler because it's already existing. So yeah, I think you can ask me if there are questions or details. So that was basically it, and I think obviously it's a very broad topic and it would be better suited for a one-day workshop, but I hope I could provide enough inspiration for people who would like to try it, but maybe were afraid of something. That if you're an expert, obviously you can just go ahead and start using it. If you're a beginner and don't really know where to start, maybe try to set up a club working group where you have access to experts, and you can have a lot of fun, and you will know what you can spend the next years of spare time on. So
very good.
That's it.
Thank you very much. Any questions for Alex?
I note at the bottom of the slide it says, with some effort with Mac and Windows.
Yeah.
What are the problems with the Mac?
Sorry?
What are the problems with the Mac?
The problems, well, the problems in general, so people who write this, I don't know if did I mention it's open source, the whole system? Okay. Both the software and the hardware is questionable, but there are schematics, so you can actually design your own version if you want it. Okay, so the general problem with this open source software in Linux is that, well, it is great software and it is written properly so that it can be ported to other platforms. And if you're a Windows user, I'm sure there are a lot of software on your computer installed which actually comes from Linux but has been ported to Windows and Mac. The problem is that there are many dependencies on external libraries, and on Windows and Mac have one way of dealing with that. They just bundle it in one package, and you have the same library installed in 20 different copies, which is why, yeah, don't have to get into it. But on Linux, they just say, okay, I know this library is installed, so we just depend on it. So when you want to port it, you have to port all the dependencies and make sure that they are there. And it works, people use it, but it takes some effort to be sure that it works properly and everything is installed. Currently with the Mac, it's a problem to make 64-bit builds. Okay. And it has become a problem with Snow Leopard.
Yeah, that's what I do for a living, so that was the question.
Yeah.
Thank you.
So,
Okay. Any other questions? Cost. How do we get on?
yeah, well, you just go on the web with a credit card.
Oh, that's not good.
Yeah, sure. It's a good question, but actually I included a slide with links for reference later on. But there is the USRP, the main board is, which you can see here. That's $700. That's from Ethos Research. You will find it somewhere here. This one. So that's $700. You will also need some RF front ends, which are available from DC to 6 gigahertz almost, with some holes in it. They cost typically between $100 and I think the most expensive one is $450. So it means that to get the main board and one daughter board, you will probably have to spend $1,000. Okay, which is a lot of money, I know, but if you want to have this performance, it's, I mean, really, it's, so I'd say about $1,000 to get started with.
But the average cost for a software radio.
But this is, I mean, this is your radio. You can use it, you can build what you want with it, okay? Mm-hmm. You see, I chose FM radio to video transmission.
Yes.
Huh? Which show me another radio which you
can't.
do. Yeah.
I think I'm just going to cut off there.
Yeah, no, sure. Yeah.
you're going to be around anyway for questions over lunch, whatever.
Yes,
'cause we can
I'll,
actually get back on schedule. If
yeah,
you're
I'll be
finished.
also here tonight and
Very
tomorrow morning.
Okay, Alex, thank you very much indeed. Thanks for coming.